All right, so past couple of class meetings, we have talked about what an agent is. We've talked about things about the environment. All right, so what do we have? We have an agent in an environment, and then we have a problem to solve. And so we're going to be, again, go through these steps to be a little bit more formal with it, and then we're going to not really focus on the formal aspect. We're just going to kind of keep that in the back of our mind as we're solving various problems. So I said that before you have solved we had done A star or we had done Dijkstra's algorithm, and now this time when you're implementing it, I want you to think of it as you're going through from this kind of AI perspective that our authors are talking about. And so when you think about the problems themselves, think about them in this context. I mean, we already kind of are just in solving the problems, but make it a little bit more precise, a little bit more formal. All right, so a problem has five components in this context. Excuse me. So the first part is we're thinking of this in an environment. So right now, the kind of environment that we're actually thinking of is probably discrete. Um, when we're looking at the search kinds of things that we've been looking at so far, it's been a discrete situation. So what do we have? We have an initial state. We have a collection of the actions available to the agent from each given state. So we have a start state, an initial state, the things that the agent can do. If it's in this state, it can do this. If it's in this other state, it can do this, and so on. We have a description of the outcome of each action. This is what we call our transition model. We have some kind of test for the end goal. Is this given state a goal state of what we're trying to achieve? Is this a state that represents where we're trying to go? So some kind of way to test that. And then there'll be one more part in just a second. But what does this sound like so far? We have an initial or a start state. We have some transitions to other states, or maybe back to that same state, but some transitions with with the different actions and what they can do. And then we have at least some state, at least one that's a goal. Um, so what does it sound like? An automaton, right? We have a start state, a collection of states, how you transition from state to state, and a target. So often we can take problems that we might not think of as we might not immediately think of them in automaton terms, but we can create that kind of structure. And so what does that do? That can help us make the decisions, right? Let the system, right, design what's going on and let the system make the decisions, and we don't have to uh, be as well. It's just more organized. That's the key there. And then the last part of this is a, a path cost function that may not be part of every single problem that we deal with. Sorry, you all can't see that. A path cost function is going to just assign a numeric value to each path from a given initial state to a particular goal state. And when we talk about the path cost, each action might have, or each step might have some kind of cost associated with it. So doing this action at this while you're in this state has some kind of cost associated. If you do that action in that state, you have a cost. It's not always the situation that you can just add those costs up, but usually, in our cases right now at least, it is. So you just add up each one of those steps, the cost of each step, and that gives you the overall path cost. Again, sometimes we don't need to worry about that portion. If the goal is just to get to a given state, then we don't have to worry about the cost. But if we're trying to get to that state kind of in the best possible way, then that does matter. All right, so what is a solution to a problem? A solution to a problem is a sequence of actions that you can take leading from an initial state to a goal state. And then an optimal solution is one that has a minimum path cost, right? So a solution to a problem right? So what happens if you can't go from the given initial state to a goal state? Yeah, then there's no solution, right? What happens if there's more than one way to get there? Well, that's where we can talk about an optimal solution. And an optimal solution has a minimum path cost, right? So so can you repeat that question? Okay, so in what happens is often we have to think about what a state is, right? So what would in that situation, the idea is that the AI is supposed to gather uh, as many resources as possible in some given time period. So what would a state, what would the start state look like in that situation? No material. And then what would happen? The actions available would depend on whatever the environment was, but maybe the AI is allowed to, the agent is allowed to pick up things. And so it looks at these actions and it starts picking up those things. Well, that's the actions available. It can pick something up or not. What does each action do? Well, if it picks up this thing, maybe it adds this much, or maybe it takes away, right? Maybe picking up certain things is a negative performance measure in that way. Um, the goal, what would a goal be? What would a goal state look like? Yeah, so that would be where to if it's unknown, right? Like what is available or how much we can hold. Maybe the agent has a maximum amount it can hold. And so a goal state would be maybe trying to, do you have the maximum amount? But that's going to depend exactly on what the other conditions are, right? But we can take just about, well, not just about any scenario, but lots of scenarios we can turn into this kind of thing, right? Thinking of, here's a state, here are the actions, here's what happens if you do those actions, what are you trying to get to? Now, if you're just trying to maximize something, then it makes it a little tough in this scenario because we don't really know what a goal state is. Is it more than you had before? Well, maybe, but maybe that's still not maximum, right? And it might be if we have competing requirements that we can only carry so many things, but some of them are more valuable than others, that we don't want to always pick up everything in order to reach that desired goal of most. Um, but the idea is still kind of there, right? It gives us a sense of we're here and we're trying to figure out how to get to what we're going to. And so this idea is, I mean, it's kind of what we think about with solving problems anyway, and we can make this work in kind of continuous things as well. Sometimes in terms of what's the state, what is happening. Remember, we had all those different conditions of the environment, and in some cases, it's a little less clear um, how we make the transitions or what happens. What is involved there. If things are changing, even though you haven't done something, we know that the transition model would be more complicated. Because you like, what happens if you're in a state and you don't do something, but you end up in another state? What kind of automaton allows that? Yeah, you have a lambda transition, right? So, and it happens to you. You don't get to choose that. It happens to you. So you're in a state, and then you just transition to another state, even while you were deciding what to do in that first state. Oh, so suddenly you're in another state, and you have to refigure. So this, you can make this idea work in a lot of situations. Um, there's probably something that we could come up with that we couldn't really make all the pieces match up somehow. I can't think of anything right now. Right, just about everything I can think of, we can make it fit. Now, do we want to? Do we want it to fit? That's a different question. But when we're creating or formulating a problem, what we have to do is abstract away parts of the real world. Right? If we're trying to solve an actual real world problem, we can't always we can't always solve the actual real world problem, not with the resources we have available. So what do? Throw away the parts that don't matter. So we had talked about the idea of a taxi. We have an agent that's driving a taxi. What do we abstract away? I mean, we care about where we are and how we get to where we need to go, right? We don't worry about things like what song is on the radio. What did you say? We do worry. We do worry if people are in the road. We at least we should. We don't worry about necessarily if the task is just the driving portion of it. We don't care how many passengers there actually are. There might not even be any passengers, and we might be going to pick up a passenger, right? So the number of passengers, as far as the driving aspect, isn't important. Um, there are lots of things that aren't important. Does it matter whether the sun is shining? Now that could affect the cameras, or if it's not shining, that could affect, if it's raining, that could affect something. So there could be times when that kind of thing might matter. Um, so there's a lot of times where things could that we can't completely abstract away, but then there are other things that we can. And so what do we have to do? We have to decide what can we turn off in terms of the real world aspect to achieve our goal. So these states might be simplifications of real life, but still then be applicable in real life. So often what we do is we use to kind of understand this and do things with it, we use what are called toy problems, right? Things that aren't really a real life problem, but they're ways for us to develop algorithms or understand concepts and deal with certain things. Turns out that sometimes these toy problems end up having their own applications and become real world problems. So solving that toy problem actually lets us solve something in real life. But sometimes they don't, right? Sometimes it's just a way for us to learn how to implement algorithms or to think about something or to see where problems will show up in other real life things and so on. So we're going to look at a few of these toy problems. Some we've seen before. And at least one I don't think you have. I mean, you may have, but it's kind of new to me, other than in this particular context. I've not seen it outside of this particular setting. So I'm sure that lots of people have thought about it before in other ways, but we'll see this in just a few minutes. All right, so what do we have? Basically, a problem. It looks an awful lot like a finite automaton, right? It can be if we have the discrete and static environment, then it's more of a DFA. If we have a dynamic environment where you just shift states while trying to figure out what to do, then we might have an NFA. But uh, the idea is very similar to what we've seen before. And then we're going to come back in later situations and actually blatantly use an automaton to build our AIs to do certain things. All right, so let's take a look at a toy problem that you've seen before. I probably should have kept that part and erased that part, but oh well. A problem that we've seen before is the eight queens problem. The idea of the eight queens problem is we have an 8 by 8 chessboard, and the goal is to place 8 queens so that no two are attacking each other. None of the 8 are attacking anything else. This is what's called independent queens, right? They're all placed in ways that none of the queens are being attacked by any other queen. They're not attacking anything. They're not being attacked back. I mean, of course, a queen, if it's being attacked, is also attacking back, right? So place 8 queens, and we've solved this problem before. You've seen it. Um, Solving the 8 queens problem. But we're going to think of it from this context, right? From this approach. So we have two different ways that we could, two kind of standard ways that we could think about building a solution. When the first time you ever saw this problem, what did you do? How did you tackle it? What did you do first? Now, before that, we drew a chessboard, right? We drew something to represent an 8 by 8 chessboard. And then what? Then we started putting a queen on. We put a queen somewhere, and then put another queen, and another queen. So what was our start state? Yeah, we started with an empty chessboard, right? So you think of it as like an empty state, right? So the initial state was an empty chessboard. And then we added queens to it. until we couldn't add anymore. Right? This approach is an incremental approach. Start with an empty state. And add queens one at a time. So what are the actions available to us? We can add a queen to an open space, right? Um, what does the transition model do? Well, in that case, the transition model says, okay, well, you've added the queen, right? Now here's your new state. You add the queen, here's your new state. What's the goal? The goal is to end up with 8 queens at the end that aren't attacking each other. We know that you can't have more than 8 on an 8x8 board, that because you can only have 1 queen in each column and 1 queen in each row. Um, and so the incremental approach starts with an empty state and adds queens to open spots, right? That's what the moves are. That's what the actions are. That's what's allowable. So what would an actual state be then? So the initial state, the start state, is an empty, no queens. What are the valid states? You can have anywhere from 0 to 8 queens, right? But you also then have the board itself. Where those queens are matters, but the number of queens is anywhere from 0 to 8. All right, so let's think about this incremental approach. Starting with an empty board, nice square board, perfectly drawn. We have this 8x8 board started empty, and we start putting on queens. We were looking at the crossing the bridge problem, and we said how many potential solutions are there? How many sequences, how many valid ways might there be to solve this? Well, if we're just putting things on here, we're going to end up always only going from state to state, but what might happen in a bunch of those? In a bunch of those approaches, we don't get to a goal state, right? We end up not being able to get all 8 queens on. So a bunch of ways of putting queens on this board do not lead to good solutions. For instance, if I put a queen in the upper left-hand corner and then put a queen right beside it, that's valid as far as a move goes, but it's definitely not heading toward a goal state, right? So, but what happens if we just consider how many ways are there to put these 8 queens on the board? So in all, just how many ways are there to put 8 queens on the board? Right? We could think of it in that way, just of placing 8 queens, 64, choose 8 ways to place 8 queens, right? There's 64 squares, choose 8. The order that you chose them doesn't matter. Right? It's that particular square, though, that you've chosen, right? That's a lot, right? 64 choose 8 is a really, really big number. Now, if we're really thinking of this from this approach, is it really choose 8? It's not really choose 8 because what did you do? You did that selection in a particular order, right? So it's like we did this action, then we did this one, then we did this one. And so we didn't choose all 8 spots at once. We chose them in sequence. And so it's a permutation instead. And what happens, that would be, what, 64 factorial divided by 64 minus 8 factorial. So 56. So 64 factorial divided by 56 factorial, because we did it in a particular order. Now, the end result is the same as if we had done it in a different order, but because of what we actually did, right? You do this move, and then you do this move, and then you do this move, and then you do this move. There are this many things. I did this calculation to see how many there are, and there are that many. Now, what do we know about a lot of those? A lot of those are wrong, right? They are not goal states, but those are possible sequences of things. Now, a lot of those end in non-goal states, right? Not 8 queens, but something smaller. But if we just start placing queens, that's what happens. And that's not what we really did, though, was it? We didn't really just start placing queens. We didn't place queens into every square. We only placed queens into squares that weren't already being attacked, right? But this approach just says incrementally start with an empty state and add queens one at a time. There's that many things that we can create from there. This is about 1.8 times 10 to the 14th power. Right? There are a lot of digits in that value. Let's see, what number is this? 178 trillion 462 billion 987 million 637,760. Okay, so if we did the choose 8 version where we pick them all at the same time, it's a lot smaller, right? A lot smaller. Still a big number, but a lot smaller than this. All right, so this is an incremental approach. Consider all 178, what did I say, 178 trillion, give or take a few hundred billion. Um, okay, so we probably don't want to try to solve this problem in that way. Because what happens with an awful lot of those, they do not lead where we want to go. All right, so what could we do instead? Instead of that, let's see if we can have a better strategy. I had one really poorly drawn board, so I decided to draw another really poorly drawn board.